Watkins. I'm going to talk about my work with analyzing the bulk flow using the cosmic flow support data, and I'm going to talk about the tension we're finding between the bulk flow and the cosmological standard model. This is the paper that this is based on, so you can see all the details there. Okay, so first off, just some basics about peculiar velocities in bulk flow. So a galaxy's redshift contains the Doppler shift portion and also a cosmological redshift due to the stretching of space. And so to extract the Doppler shift part of that, to extract the peculiar velocity, you need to subtract the cosmological redshift from the measured redshift. And so this gives us the radial component of the galaxy's velocity along the line of sight. And because of the R being in here, we need to measure the distance of the galaxy, which is generally difficult for faraway galaxies. So some of the challenges to working with peculiar velocities, first off, we can only measure this radial component, so we can't get the full 3D velocity. The distance uncertainties are typically a percentage of distance, and so what happens is that once you get even to reasonably large distances for galaxies, you're going to find that you have incredibly kind of ridiculous large uncertainties for the individual peculiar velocities. And then another factor we need to account for is the fact that if we're going to make assumptions, if we're going to connect this to the models, the linear model for the velocity field really only applies on a large scale. So somehow we need to average out those small scale velocities. So the way we're going to get around those problems is by analyzing the large scale bulk flow. So what is the bulk flow? Well, we take a region of radius r with a bunch of galaxies in it. This is not real stuff. This is the Hubble deep field. But imagine that those galaxies, we have velocities for each of those galaxies. And to measure the bulk flow, what we have to do is average those velocities to get the average velocity of that volume. And this is, of course, a function of the radius of the volume that we're looking at. So some of the advantages of the bulk flow, so we're going to average out these large measurement errors. So even though the individual velocities have huge errors, when you average all the galaxies in the volume, you can get smaller errors for the bulk flow. It also averages out the small scale nonlinear motions, and so we don't have to, we can apply then linear models to analyze the results. This provides a test of the cosmological principle. If the universe really is homogeneous and isotropic, then the bulk flow should get small as you get to very large radii. And then also this measurement can be made independent of the Hubble constant, h0. So even though h0 appeared in our formulas for the peculiar velocity, that adds a constant radial velocity to all the galaxies. And if you have a full volume, then when you average over that constant radial velocity introduced by changing the Hubble constant, that can go away, that can average out. So this measurement should be, even though we need to use the Hubble constant to find the peculiar velocity, the measurement itself is independent, can be made independent of the value of the Hubble constant. The disadvantage of working the bulk flow is it takes an entire data set, which is lots of information, and reduces it basically down to 3 numbers, the 3 components of the bulk flow. Let's see. This stopped working. No? Oh, that's not the right. Oh, I'm sorry, that's the wrong one. Can you advance the slide one? I don't know why this is stopped working.
Can you try it?
Okay, there it is. Okay, so mathematically, the way we calculate the bulk flow is we basically do a weighted average of the radial velocities. So each direction, x, y, and z, is going to have a different set of weights. And then you're just going to sum the radial velocities times those weights to get the three components, ux, uy, and uz. So for an ideal survey, it's a cool mathematical fact that if you use these weights, so if you just take the component of the radial vector along the component of the bulk flow that you're trying to measure, and you weight by a 1 over r squared weight, you can show that mathematically that will reproduce the bulk flow calculated from the full 3D velocity. So if you had an ideal survey and you only had radial velocities, you can still reproduce the full 3D bulk flow. So you can still reproduce what you would get if you had the full three-dimensional information. And the reason you can do this mathematically is just because the velocity field is curl-free. So we're assuming that the velocity field is created through gravity, and that suggests it should be curl-free. If you use a curl-free velocity field, that is that's a potential field, and so there's really only 1 degree of freedom there. There's one piece of information. So the radial velocities, in principle, carry all the information of the full 3D velocity field. If it's not 3D, if it's not curl-free, which pretty much everyone assumes it is, but if it isn't, then this still gives you an interesting moment in the velocity field. It just doesn't necessarily represent the same thing as that 3D velocity. Okay, so real surveys, when you look at real surveys, they don't sample the volume very evenly. You have generally most of your information from your survey is going to be for nearby galaxies. Not only are there more nearby galaxies, but not only do the sample tend to contain more nearby galaxies, but they also have smaller uncertainty. So most of your information is concentrated in the center of the survey. And so that means that if you just calculate the bulk flow naively by averaging over those galaxies, you're going to basically overestimate the nearby galaxies are going to have a bigger influence than you want. So I've developed this method called the minimum variance method that generates weights that estimate the bulk flow in a way that's as close as possible as it would be to an ideal survey. So if I have this collection of galaxies in my volume and they're unevenly distributed throughout that volume, the information is unevenly distributed. We also account for the differing uncertainties of the galaxies. Then it will essentially even that information out and get you as close as possible to what you would get if you actually had an ideal survey. Okay, so a bonus of that method is it's easy to add constraints to the minimum variance method to ensure that the bulk flow estimates are independent of the Hubble constant. This is essentially we're flattening out the angular distribution. If you have a change in the Hubble constant, you want it to add, that introduces a phantom radial flow to your survey. What you want to do is make sure your survey samples all the directions evenly, and that will ensure that you're going to average out that effect of the Hubble constant. So the method, it's easy to add a constraint to make sure that that happens, so that you don't end up having the Hubble, the phantom radial flow reflected in your bulk flow. Okay, so there's, now I'm going to switch gears and talk about the data I worked with. So distance of galaxies are typically measured through the distance modulus, mu, and that has an uncertainty delta, which is generally assumed to come from a Gaussian distribution. So when you take the 10 to that, to calculate the distance from the distance modulus, when you take 10 to the mu over 5 minus 5, it turns out you can show mathematically that that has a statistical bias in it, that generally overestimates the distances. And so I've come up with this method of correcting for this overcompensation. So you can just multiply it by this exponential where you put the width of the Gaussian distribution, the size of the uncertainties in there, and this corrects for it and makes sure that the average radius is in fact equal to the, on average, the radius is centered on the true radius. So it scatters around there, but it's centered on the true radius. So that's new in this paper. I've played with different methods in the past, but this one seems to be the best method for doing that. So it does correct the statistical bias, but it does introduce a non-Gaussian error distribution. But it turns out that in our calculations, that doesn't really matter. Okay, another aspect of this data is that galaxies basically have been identified for being in the groups that they're in, and then basically the distance moduli have been averaged, done a weighted average to make a single more accurate distance modulus for the group as a whole. So basically the data is divided into both single galaxies and galaxy groups, and that also tends to eliminate some of the nonlinear motions in the survey. Okay, so what's the data look like? So Cosmic Flows 4 now is up to 38,000 individual galaxies and groups. So I'm using the group version of the catalog. There is a individual galaxy version of the catalog, but it makes more sense to use a group. So each galaxy or group has a redshift measured, a distance modulus, and then an uncertainty in the distance modulus. And so you can see that the original Cosmic Flows surveys 1 and 2 were more isotropic on the sky, but the Cosmic Flows catalogs have been becoming more and more anisotropic as time goes on. So for CF4, it's very anisotropic. There's lots of galaxies in this. This is the galactic coordinates, so this is a zone of avoidance here. And you can see that we've got lots and lots of galaxies on that north galactic side of the map. And this is due basically to the SDSS being added to the survey. So this is now, or to the catalog. So this is now the Sloan Digital Sky Survey, which we know is not a full sky survey, but actually just has a patch of the sky, and that's where all these galaxies are. Now, this isn't necessarily where the information is, though, because the SDSS galaxies are very distant. And so there's less information in these galaxies than you would think, but it's still important to take that into account. There's also the 60F galaxy survey is also included in there, and that's also kind of fairly anisotropic. And then the rest of the galaxies there's a very large set of Tully-Fisher measurements that have been done over the years that have been added to this as well. So basically the data has become very anisotropic and very weirdly distributed in the volume, and so it's even more important to be using something like the minimum variance method to even out the data, to even out our sampling of that volume. Okay, so radially, what's the distribution look like radially? So this is versus distance or versus redshift, depending on what you want. And this shows how the galaxies are distributed. This is like the SDSS is way out here. Between most of the galaxies are out here between 2 and 300, and so this looks fairly even. Notice that if we had a full sampling, ideal sampling of the volume, this would go up like like R squared, because there's more volume at larger distance. But it's still nice that we have a flat distribution, but it's important to keep in mind that this is not isotropic on the sky. So most of these are in the northern galactic hemisphere, and then the rest are fairly more evenly distributed around the volume. So the question is, how big can we go? And to figure out how big a volume we can sample and get close to the ideal survey, we look at what are called the window functions. And the window functions tell us how the sample is, how it's sampling the power spectrum. So you can see at 100 H inverse megaparsecs, So the solid line is a real survey, and the dashed line is the window function that the ideal survey would have if we had one. So here's at 100 megaparsecs, you see the minimum variance method basically weights the galaxies so that we basically have, it samples the power spectrum in exactly the same way, or not exactly, but close to being the same way as the ideal survey would. So if you just took the window function of the galaxies, the raw galaxies without the weighting, then it would be very different than this. But the minimum variance method essentially compensates, evens out the survey so that it matches the ideal survey. 150, it still matches pretty well. At 200, you're starting to see a divergence here where the real survey can't quite match the depth of the ideal survey, and then at 250, it's way off. And so I think the 150 is about the best, and then I throw the 200 megaparsec results in there too, just to consider that. Okay, so here's our results, and this is where things get interesting. Notice that these are the bulk flow components, ux minus uy minus uz, and the magnitude. And something strange is going on. This red curve is the theoretical expectation for the bulk flow. And the bulk flow should be declining as you go out to larger radius, but instead we see it rising. So the bulk flow is actually getting bigger with distance in all three components. All three components are essentially getting a little bigger. So this is a weird state of affairs, and we don't totally understand why this is happening, but we see it, even if we split the survey, the catalog up into its various components, we see the same effects. So this is not just an effect due to some of the galaxies, but it's actually the whole sample is contributing to this effect. It's not only does it increase with distance, but it's also increasing in magnitude. It's much larger than expectations. So this is what it should be, is this red line. This is what it is, this green line. And the direction of this, you can't see that from here, but if you look at these components, the direction is roughly in the direction of the Shapley supercluster, which is kind of what you would expect for the bulk flow of this volume. We did a chi-squared analysis with 3 degrees of freedom just to figure out, to compare it to the standard model using the Planck CMB parameters. And you see that as R increases, the bulk flow becomes increasingly unlikely. So this is a probability on a logarithmic scale. Notice that the probability is going down with distance, and this means that if you have a different analysis, people often talk about the bulk flow, but there is no bulk flow. The bulk flow is a function of radius, and so if you were to analyze a smaller radius volume, your bulk flow would basically, you could say that it's consistent with the standard model. So you only see the deviation, you only see the tension from the standard model when you get out to these larger radii. And so if someone tells you that the bulk flow is consistent with the standard model, you have to ask them how do they know what scales they're probing, and how do they know that they're actually seeing these large scales? Because the problem only comes out on this large scale. So just to summarize those results, we get a probability of about 1.5 times 10 to the minus 4 at 150 H inverse megaparsecs, and then at 200 it even gets worse here. So the tension that we're seeing is about the 3.8 sigma level at 150 H inverse megaparsecs. So this is becoming worrisome. So it's been getting worse and worse as we've been getting more data. I put the 200 megaparsec result up here also. It's at the 4.8 sigma level, but I'm not as confident in this result. But this is something that I'm pretty confident in, this 3.8 sigma level. So one explanation of this could be a violation of the cosmological principle, and this has been seen in the distribution of quasars. And that's something I've been thinking about. It's also, obviously, this could be something in the data, and so it's some systematic in the data. So it's important to continue to improve the data set and the methods. And here is my paper again, the archive questions. Go ahead and, let's see. Okay, this is
It's perfect.
Yes.
Okay, Richard, is this consistent with the dark flow claim with Watkins, which is 300, yes, 300 inverse? And also, is this consistent with Costas Mikas and all finding analysis properties in galaxy clusters, scaling relations, right? You haven't mentioned these two results, but it sort of says once you get to those larger scales, which are roughly 508 parsecs, you expect to see this.
Right, so Kashlinsky, you can't really compare to that because that's on a much different scale.
But I thought it was like 300 divided by h parsecs, right?
I think his is actually much larger than that.
But 500 megaparsecs is the scale I have in mind.
Yeah.
Now, so Costas is at 500 megaparsecs.
So I'm not, I don't know that work. I should look at that paper.
Right. We also have a review on FLRW that covers all of this. Probably covers some of your work as well.
Okay.
So it's all in there, right?
Cool.
There's a question, yes, yeah.
Oh, yeah.
Thank you so much. Yeah.
So Martin Astor is asking, could the large bulk flow be due to a massive supercluster behind the shape ring? If yes, then this might be another tension in ΛCDM, too many massive superclusters in the local universe.
Yes, I think that's possible. That it could be indicating that the distribution of mass on very large scales is inconsistent with the standard model. Yeah, that's.
Thanks for a very nice talk and paper. I was wondering, like, for given the very, given the quite low error bars that you have on your final results.
On the error bars on the magnitude of the flow?
Yes.
Yeah.
I think one should start worrying about, correction terms of order z times v in the formula on page 1.
Do you mean
This one.
Oh no, you mean no, the correction?
I mean in the formula for the outflow, the Hubble law.
Oh, in the Hubble.
It's just not a approximation, yes? This is
Stack.
Yeah. So that's the correct lowest order cosmographic expansion.
Right.
But you're going to have both like classical Newtonian motion effects and general relativistic effects on time dilation and so on that are all going to be times sets.
I did correct, I didn't mention this, but I did correct the cosmological redshift for the acceleration, the accelerating expansion. So it is, I do use a correction, the general physics correction at large.
Yeah, but I don't mean that one, I see what you, I see what you mean. So, but that's a vector as well. But there's also there's both just classical motion effects that are going to be in time sets terms and time dilation effects, because you have the gravitational potentials are going to that actually generate the bulk flow are also going to give you intrinsic effects in the photon propagation.
Right.
But I'm not saying that that your end results. This will be sort of order 10% effect. So it's not your conclusions are.
It's not going to fix it. Yeah, but at this point the error bars are getting small enough that we should be taking into account more corrections.
And also a question. So is it the correct interpretation that if we say that there is indeed a plateau towards the larger scales, as your results sort of hint,
So I think the plateau is kind of misleading, actually, because once you get out to these distances, we're not adding much more information as we increase. Especially, I take that to 250 there, but as you go out, like between 200 and 250, there's not that much more information. So it actually is starting to deviate from the real, the ideal bulk flow is starting to deviate out here. And so that could be continuing to go up, or it could be coming down. So we need more data on these large scales.
Right. Okay, but if you take the largest, if you take the velocity at the 200 passes scale, so like 400 kilometers per second, is it the correct interpretation that, so this is in the CMB frame, is it the correct interpretation that that would be something like 800 kilometers per second in the heliocentric frame? What's it say?
I have to think about it.
I have a feeling that we are getting a very
Yeah.
technical level, so maybe we can continue. There's one more question from
Yes.
someone.
Yeah.
Okay, so maybe
This is Neriman Iyaz Mayga asking, what about the experimental part of this idea?
What about what?
What about the experimental part of this idea?
The experimental part?
Yes. This is what
So, do you mean in terms of the data? What?
is this what you mean?
Yeah, so one of the collaborators on this work is Tully, and he is the person who put the cosmic flows together. And so, it is possible that there's a systematic in the data. But we did do a lot of checks to eliminate the idea that maybe a few galaxies were causing a problem or a particular type of galaxy. So we divided it up into the different distance measurements, the Tully-Fisher sample, the fundamental plane sample, and checked that all the different subsamples give basically the same results.
okay. I think we have to close. Yeah, yes. So thanks again, Richard.